Thank you for having me. I want to talk today about a device that we have built. We call it Bodytune, which is a digital and AI-enabled auscultation device, so a listening device. And we believe that it could be used for prediction and monitoring of several diseases. So we combine with this one auscultation, the listening, with the segmentation of the individual information that we see. We classify it. We use AI to actually create classifying parameters, and again, used for monitoring and prevention. I want to acknowledge all the people that worked on this device. And also the parties that are involved with it. It's a university-based research topic done together with an industry partner and some other startup companies that are part of our chair. So just to start with what we initially thought, what we would want to do is to actually monitor the carotid arteries. And why? Because carotid arteries can cause, several problem areas. It can cause several problems in the brain, as many of you know. Plaque can build up, then can actually reduce the blood flow, can lead to less oxygen in the brain, can lead to strokes, all kinds of things that can happen. And it's very important to be able to monitor the disease stage or the build-up stage, and maybe even do preventive, use a device if you could use it for monitoring, for prevention, and for actually status assessment. So what we have built is, and we thought, sorry to get back up on this one, we thought that using something at home, not going to the clinic, at home, where you can actually have a device that you put on and use for this monitoring would be quite helpful. And as people don't have ultrasounds at home and cannot actually use them most themselves, we thought about auscultation, which is actually listening to the sounds that come from the body. And in this case, a device where we use MEMS sensorics and hold it close up to the carotid, listen to the sound, and then see whether we can actually get meaningful information out of this. So this was our first device. It's about 2 years ago. I presented that at SMIT 2017, I think. So first device, quite rudimentary, quite complicated because we had a sensing unit on which was not really good. We compared that initially and used it with a stethoscope device, and kind of like try to resemble a stethoscope device by building an electronic setup. Now, what one of the initial ideas is that we actually try to compare a carotid pressure waveform that you obtain by ultrasound with carotid audio signals, and see on whether there is when you can establish a correlation between those two signals. And for that, you need to actually have fiducial points to simulate, to actually find starting and ending points. And we used a rather complicated algorithm and set up to extract these signals and to segment these signals and put them over each other. And what was very interesting to see, you use these points for the auscultation and the flow signals, that you actually can see different information on the flow, on the auscultation sound, than you can use on the Doppler sound. So if you look at the bottom part, you see there's also 4 different subjects. They all look pretty much the same, but the actual auscultation sound even in some segments significantly varies from the Doppler information. So that was bringing us to the point that we believe we can use this information to characterize individual flow profiles and maybe even use it for biometric information. So this was some of the initial work we did. We then used time varying power density spectrum analysis, also autoregressive modeling technologies, and also polar energies to extract information from the audio signals that we obtained, focusing on lower frequency, medium and high frequencies, and all kinds of other things, just to find classifiers that would allow us later on to be able to really judge and determine a particular profile. So you see here on the left side, you see 2 individuals, and you see how the signals look like, how the time varying power spectrum density looks like, now the pole projectors look like. And you see there are significant differences between those two individuals, do both, by the way, healthy individuals. So that made us believe that we can actually use this auscultation, audio signal listening, to use for biometric information and for actually monitoring. Because if you see a change and a difference to your own information that was obtained maybe half a year ago, you can possibly then later on, using deep learning approaches, evaluate on whether things have changed to the worse or maybe to the better. So we have, in the meantime, improved the system significantly. We're using now 2 microphones, membrane microphones or non-membrane microphones, and it's kind of like almost a stereo approach, but it's not used in that sense. But these microphones also now allow us actually to relatively well get rid of the ambient noise and just focus on the auscultation sounds that are directly coming from the carotids. This is the setup of the device. We have connected it via Wi-Fi to a desktop application where we can then look at the signals in more depth. What we want to do in the next few months is that we actually create a local setup where we can determine already whether the signal quality is sufficient or not, and do a little bit of a pre-evaluation. But for the subsequent segmentation and evaluation, we would send the data then to a desktop or to a cloud application. So this is how the system looks at the moment. There's these 2 openings for the sensors you see on the right side. There's some status slides. We don't have to go into detail on this one. It's a fairly easy setup, which shows you whether the system is able and recording or not. And we will also now put up a light and indicator, which makes, whether it's just previously said, indicates on whether the signal was obtained properly and was of good quality. So this is how you place the setup. This is even the newest model that we did. So we have some iteration processes. I think it's prototype number 5 we do. This is Ritucha, one of the engineers who's actually developed the hardware, putting it and showing the signals that you obtain directly. There's this little yellow part on the bottom you see on the screen. I'll point out to this in a little while, because what we figured out, it's not only possible to actually listen to the carotid flow sound, but you can actually listen to many other sounds that come from the body, and they may help us to extract more information and get more hints on the health status of the user. So this is what it is. Let me just go to this in the next couple of slides to illustrate what I mean by that. So this is a more detailed analysis of the signal. You can now scale it up and down. Everybody knows how to do this. This is the second scale. This is is a very accurate information that you can obtain, and then you can also assume, looking at this signal, that there's lots of information you can extract by using advanced signal processing techniques. So this is, for example, let me just go back one second. This is, for example, a non-standard signal. This is the standard signal. You already see it's a little smoother, so we also believe that you can actually use it to determine when the right point is to use standing, and maybe to monitor a disease that is ongoing and determine when is the right point, and also to monitor on whether a stent is working properly and maybe becomes stenotic at some point in time. So here's the signal that you can actually extract and widen, and you can get quite a bit of detailing. You also see that there's relatively little noise in this signal, which makes us also believe that the information extraction is, after the filtering that we do, is quite usable for further deep learning approaches. This is what I said before. So what we do now is we actually acquire data streams that are, there's a little sequence behind that. So we start with the normal breathing through the nose, then we have some non-breathing approach, then we do some controlled respiration. swallowing sounds and also some coughing sounds. So we hold the device there and cough into it. And we also, feel that we can actually evaluate. Maybe it could even be used for some COVID-19 related evaluations, or at least a distinction on whether a potential patient has a normal cough, maybe some pneumonia or COVID-19 or other coronavirus related cough symptom changes. So I don't know, it's all open, but I believe that the data points that we have make us believe that we can use it. So you see the different signal qualities that we have. The green signal you see at the bottom is basically similarity measures. The red is an envelope of the signal. So that there's different type of strategies that we have of evaluating and analyzing the signal to be able to segment the data points out of it. If you look at the red signal, you clearly see there's a significant difference between the normal breathing, the apnea sounds, and then heavy breathing. So you can use this quite nicely to segment the data points out. Also, you see that on the swallowing part, you see the green line that is significantly different from any of the other signals you see. So these ones we use mainly for the segmentation points. So here's an example of when you have segmented these out, and you can now subsequently use them for the feature extraction. What a heart sound looks like, what deep breathing looks like, and what swallowing looks like. So our next steps are that we will create an app, and we'll create a better user interface, and should be able to then not only extract the data, but work on the data, compare them with other people, and hopefully get some further conclusions on what the data, the feature extraction really means. So we want to combine this also with some point of care ultrasound and with a digital twin approach, just to be able to monitor diseases. You can do things, monitor at home. You can also combine it with data points that you acquire at the ambulatory doctor's visit, and then actually create data points for your own use later on. So if you look at the trend map of what happens in healthcare, this device could actually be used for a lot of things of monitoring lifestyle, human body diseases. Would also be used for some mental stress application. Maybe you can actually see some stress related issues even on the sign. So there's a lot of opportunities, a lot of options that we believe we have not analyzed yet, and there's a good hope that that audio actually is usable for that as well. So we invite everybody to actually help us, create more data points and make this a more powerful tool. So as a summary, signal processing, feature extraction, and the classification allows us to create individual profiles. So we actually have shown that you can get biometric information, and that my profile looks different than anybody else's profile, which also means you can use it for monitoring of your own status, and possibly see on whether there are any detrimental effects developing. The deep learning, comparing with other data points, big data, hopefully at least has the possibility to use for prevention in the future. We believe also that the combination of not only listening to the auscultation sound, but also swallowing, coughing, respiration, and other things, will be able to classify and quantify diseases. So there's some hope on this one. And if you combine it with a point of care ultrasound, for example, you may be able to create data points for a digital twin. So all in all, audio is very powerful, and we're quite excited about the possibilities, and hope that you're excited as well. And this is my team. Thank you very much, everybody working on it. And on the right side, you see some of the science references, particularly related to this device. Thank you very much.